Ever stop to think about what a roaring campfire and, say, a single bite of an apple actually have in common? It's a great question, and it really gets to the heart of this hidden engine that powers pretty much everything. So today, let's build a little mental toolkit to really understand that engine: energy.
You know, when I first heard this question, I was stumped for a second. I mean, one is this huge explosive release of heat and light, right? And the other is, well, it's the quiet start of a biological process. But the answer is actually so simple and honestly kind of profound. It's all about the transfer of energy. And once you see it, you start seeing it absolutely everywhere.
Okay, so to really get that question, we've got to start with the basics. Let's build the first piece of our toolkit and just nail down what energy actually is. This is where it all begins.
So what even is energy? Well, here's the official scientific definition, but let's make that a little more real. Think of energy like a coiled spring. It has the potential to do something, to launch a toy, to turn a gear. That capacity is just sitting there, stored up, waiting. That's energy.
Now, this capacity really shows up in two main flavors. First up, on the left, you've got kinetic energy. Simple enough, that's the energy of motion. Think of a roller coaster as it's screaming down a track. Then on the other side, we've got potential energy. That's the stored stuff. It's that same roller coaster car, but it's paused at the very, very top of the hill, just brimming with the potential to move. A log for a campfire is just packed with potential chemical energy, waiting to be released.
And here is the #1 rule of the entire game, the first law of thermodynamics. This is so important because it tells us that energy is basically a master of disguise. That campfire isn't just creating heat out of nothing, it's transforming the stored potential energy from the wood into heat and light. It's all just a big conversion, changing from one form into another.
So we know what energy is and we know it changes form, but how do we actually measure it? How do we put a number on it? Well, that brings us to tool number 2 in our kit. This is where we get to be a little more precise.
We use a technique called calorimetry. Yeah, I know, it's a bit of a mouthful, but the idea behind it is actually super simple. Think of it like being an energy detective. We're trying to figure out how much heat moves from one place to another, and our main clue is the change in temperature. If we can measure that change, we've cracked the case. And this formula right here? This is our magnifying glass. It might look a little intense at first, but let's break it down real quick. Q is the heat we're trying to find. To get it, we just need 3 little pieces of information. First, M, which is just the mass of whatever we're looking at. Next is C, the specific heat. That's just a fancy term for a number that tells us how much of a kick a substance needs to raise its temperature. And finally, delta T. That's simply the change in temperature from start to finish. You multiply those 3 together, and boom, you've just measured the invisible flow of heat.
All right, let's put our new tool to the test. Let's solve a case. We've got 100 grams of water. That's our M. We've got the specific heat for water, which is a known constant, and the temperature change, our delta T, is just 45 minus 25, so 20 degrees. Go ahead and plug those into our formula. Take a second. What do you get?
Ready for the answer? It is 8,360 joules. And so what? What does that number even mean? It means we've just put a precise measurement on the amount of energy that flowed into that water. It's not just a vague idea of getting warmer, it's a concrete number. That's the magic of calorimetry right there.
Okay, so we can define energy, and now we can measure it. Let's add our third and final tool to the kit. This one lets us apply everything we've learned to one of the most important things in all of science: chemical reactions. This is where things get really, really cool. Or hot. So, to track heat in reactions, scientists use a concept called enthalpy. Again, it sounds complicated, but the idea is simple. Think of it like a little energy bank account for chemical reaction. Enthalpy, which we write as delta H, just tracks the heat withdrawals and deposits.
And these transactions, they only go in 2 directions. If a reaction releases heat, making its surroundings warmer, like our campfire, we call it exothermic. Just think of heat exiting the reaction. In that case, its delta H is negative. It's an energy withdrawal. But if it absorbs heat, making its surroundings feel cold, like one of those instant ice packs, it's endothermic. Heat is entering the reaction, so its delta H is positive, an energy deposit.
So let's see if you've got it. Quick question for you. Burning methane releases a huge amount of energy. The key word there is releases. So is that an energy withdrawal or a deposit? Of course, it's exothermic. You got it, right? The delta H for this reaction would be a -890. And there we go.
Our toolkit is complete. We can define energy, we can measure it with calorimetry, and we can track it in reactions using enthalpy. Now for the fun part. Let's actually use this toolkit to understand two very different but very similar engines, a car engine and the engine that is you.
First up, combustion. This is the classic example of thermodynamics in action, right? It's what powers our cars, our factories. It's a process we see all the time, and it is all about that transformation of energy.
And just look at how perfectly our toolkit explains it. First, the concept of energy. That potential energy stored in fuel gets transformed into the kinetic energy of a car barreling down the highway. Second, calorimetry. Engineers literally use this to measure a fuel's energy content so they can design more powerful, more efficient engines. And third, enthalpy. It tells us that combustion is a massively exothermic reaction, which just means it releases a ton of heat.
But get this. This is the really wild part. The exact same principles that make a car engine go are also at work inside your own body right now. It's pretty amazing to think that the same fundamental process that powers a rocket is also what's keeping you alive.
I mean, look how similar these two processes are. Your body transforms the potential energy in food to power your cells. Nutritionists use calorimetry to figure out the energy content of what we eat. That is literally what a calorie on a nutrition label is a measure of. And your metabolism, just like combustion, is an exothermic process, releasing the energy that keeps your heart beating and your brain thinking.
So what's the big takeaway here? What's the point of all this? Well, it's that these ideas aren't just for a science test. This is pretty much the instruction manual for how our world, and even how life itself, gets its power. It's why this stuff is so fascinating.
And this science is everywhere, shaping our world in ways we might not even realize. You've got engineers using it to build better cars and safer power plants. You have biochemists using it to figure out how our bodies work, which helps us find cures for diseases. And you've got environmental scientists using it to track the flow of energy through entire ecosystems so we can understand the future of our planet. So, the next time you start your car or you take a bite of an apple, just think about that incredible transfer of energy that's happening. The first law tells us energy can't be destroyed, right? It just gets moved around and reshaped. It's this constant, powerful flow moving through everything. And the only real question left is, how are you going to use your piece of it?